Imagine a stadium-sized asteroid is going to hit Earth in exactly 2 weeks. Even at that comparatively modest size, it tears through the atmosphere at 60 times the speed of sound as a fireball brighter than the sun, and slams into the ground with the destructive power of roughly 4,000 Hiroshima bombs, flattening cities and killing millions in an instant. This isn't science fiction. It's a genuinely plausible near-future scenario, and a disturbing number of the asteroids capable of causing exactly this kind of damage have only ever been spotted at the very last possible moment. In 2019, an asteroid roughly the size of a 30-story building, nicknamed 2019 OK, was discovered barely 1 day before it swept past Earth, closer than some of our own satellites. The following year, an even larger asteroid was spotted just 13 days before it passed closer than the Moon. Had either one actually struck Earth, they would have unleashed somewhere between 3,000 and 9,000 Hiroshima bombs worth of destructive energy. Here's the genuinely unsettling part. Right now, humanity doesn't really have a solid plan for what to do if one of these objects is heading straight for us. Scientists have proposed plenty of clever deflection tricks over the years, painting an asteroid's surface so sunlight pushes it off course more effectively, landing thrusters on it to steer it away, scorching it with focused lasers, or slamming a spacecraft into it to nudge its trajectory. NASA actually tested that last idea for real in 2022, deliberately crashing a spacecraft called DART into a small asteroid named Dimorphos, and successfully shortening its orbit, genuine, real-world proof that a kinetic nudge can work. The catch with every single one of these methods, DART included, is the same. They're the equivalent of trying to steer a fully loaded cargo ship by throwing a bag of potatoes at it. They do move the asteroid, but only by a tiny amount, which means you generally need years, sometimes decades, of advance warning to make a real difference. Given how many dangerous asteroids we've only spotted with days or weeks of notice, that's a serious problem. But very recently, scientists have worked out a genuinely different, far more dramatic approach, one that, remarkably, could be built with technology that already exists today. Let's walk through exactly how it would work, using a 100-meter asteroid on a 2-week collision course with Earth as our example. The whole strategy hinges on a secret weakness most people don't know asteroids actually have. For a long time, the popular image of an asteroid was something like a single gigantic solid boulder, essentially a chunk of broken metal drifting through space. It turns out that's mostly wrong. Most asteroids are actually much closer to loosely packed bags of gravel, heaps of pebbles, dust, and scattered minerals, barely held together by their own weak gravity. That changes the whole calculation, because instead of just nudging something like that, we might actually be able to shatter it outright. The obvious first idea is a nuke. So let's try it. Load a nuclear warhead onto a rocket, launch it, aim for a direct hit on the incoming asteroid, and the asteroid destroys the nuke on impact. Asteroids can barrel toward Earth at up to 70,000 kilometers an hour, fast enough to cross the entire Atlantic Ocean in about 5 minutes. No warhead humanity has ever built could survive slamming into solid rock at that speed intact. The impact itself wrecks the bomb before it ever gets the chance to detonate. Fine, try detonating the nuke just before contact instead, in the air a few tens of meters above the surface. That approach carves out a genuinely dramatic crater and does basically nothing else useful. Space doesn't have any air to carry a shockwave, so almost all of the explosion's energy simply radiates away uselessly in every direction instead of transferring into the rock. The asteroid still hits Earth on schedule, just a few kilometers off from where it would have otherwise. Hitting something that massive with a nuke this way is a lot like trying to stop that same cargo ship by throwing a washing machine at it instead of potatoes. A meaningful upgrade, sure, but still nowhere close to actually solving the problem. So what about the classic Hollywood move? Land a crew directly on the asteroid, drill a hole, and bury the nuke deep inside. That's theoretically possible, but suicidal in practice. Landing on any body in space is genuinely difficult. Even on Mars, a comparatively enormous target whose surface we've mapped almost perfectly in advance, roughly 70% of all landing attempts in history have failed outright. Now imagine trying to land a crew and a live nuclear weapon on a small, extremely fast-moving asteroid that was only discovered 2 weeks earlier. Even in the best-case scenario, where the landing somehow succeeds, drilling in microgravity turns out to be agonizingly slow, since there's essentially no downward pull, helping the drill bite into the rock. It would take far more time than a 2-week warning window could ever provide. Hollywood's version, in other words, just doesn't survive contact with reality. The actual answer requires thinking less like an action movie director and more like a lumberjack. If you want to split a heavy log, you don't just hit it with a rock, you use an axe, a dense, precisely shaped tool built specifically to concentrate force exactly where it needs to go. Scientists have landed on essentially the same idea for asteroids, in the form of super-dense, ultra-fast cosmic bullets called penetrators. They're a few meters long, slim, and built out of tungsten, a metal dramatically denser and harder than ordinary rock. The genuinely elegant part is that we never actually have to shoot them at anything. All that's required is putting a penetrator directly in the asteroid's path and letting it sit there, floating silently in space. From the asteroid's own reference frame, it doesn't matter that the penetrator is technically motionless and the asteroid is the one moving. All it experiences is something rushing toward it at 70,000 kilometers an hour. Physics doesn't care which object is labeled as stationary. That speed does create one real constraint, though. By far the longest and most demanding part of the entire mission is simply getting a penetrator to the right position in time. And there's a second constraint layered on top of that. The collision can't happen too close to Earth, because if it does, thousands of freshly shattered fragments would slam into our atmosphere all at once, and their combined shockwaves would stack together into something with the destructive force of thousands of nuclear weapons hitting simultaneously. Our atmosphere can comfortably absorb scattered individual chunks, but not a synchronized swarm of them. Instead, the ideal intercept point is roughly 1 day before impact, when the asteroid is still nearly 2 million kilometers away, more than 4 times farther out than the Moon. That's a genuinely vast distance, but a manageable one. Current rockets can cover it in about a week. For our 100-meter example, a single 2-meter-long, 2.5-ton penetrator gets positioned precisely in the asteroid's path, and then everything waits. A tiny speck of light eventually appears in the distance, and within moments, it's already here, moving faster than the speed of sound. Slowed down for a closer look, the actual collision is almost unbelievably violent. The asteroid slams into the penetrator with enough force to release energy equivalent to about 120 metric tons of TNT. The impacted rock instantly vaporizes, the tungsten itself melts away, and the combined force tunnels straight through the asteroid's structure. There's simply too much energy with nowhere else to go, and the whole object shatters into thousands of separate pieces. That debris spreads apart into a diffuse cloud as it continues toward Earth, and by the time the fragments actually arrive roughly a day later, they're scattered across hundreds of thousands of square kilometers, turning what would have been a civilization-altering catastrophe into little more than an unusually dramatic fireworks show. With proper preparation in place beforehand, a 2-week warning window would genuinely be enough to pull this off. But that's still just a small asteroid. What happens if the threat is a genuine cosmic mountain, a true planet killer carrying the combined destructive power of tens of thousands of nuclear arsenals at once? The non-avian dinosaurs could tell you exactly what that looks like, if they weren't, notably, no longer around to ask. Planet killers are objects large and powerful enough to end most complex life on Earth in a single strike, and the most dangerous versions of them are comets arriving from the distant, frozen fringes of the solar system, so far away and so dark that reliably tracking them in advance is close to impossible. Unlike solid asteroids, comets are essentially dirty ice balls the size of mountains, more structurally fragile than pure rock, but traveling dramatically faster, often around 140,000 kilometers per hour. In 2020, the real comet Neowise, carrying an estimated 6,000 times the combined destructive power of every nuclear weapon on Earth, was only discovered about 4 months before its closest approach to our planet. So the genuinely frightening question becomes, what if we found something like that, but on a collision course with only 6 months warning? Could we actually survive it? Unfortunately, that scenario runs into several serious problems at once. First, a planet-killer comet carries so much more raw mass than a small killer asteroid that simply shattering it into a few million pieces, the same trick that worked earlier, wouldn't actually help much. The individual chunks would still be massive and numerous enough to set the sky ablaze and wipe out most life on Earth regardless. What's actually needed is for nearly all of the resulting fragments to miss Earth entirely, which means the intercept has to happen much farther out, roughly as far away as Mars's orbit. And destroying something mountain-sized at that range requires far more than a single penetrator, realistically hundreds of thousands of them. Transporting that much mass that far out would require at least 24,000 super-heavy rockets. As of right now, humanity has exactly two, and neither one is even fully operational yet. Even in a scenario where every industrial resource on the planet immediately pivoted to nothing but rocket production, we still couldn't finish building that fleet in time. Put plainly, if a genuine planet killer were spotted heading our way today, there would be essentially nothing we could actually do about it. Except, possibly, for one remaining option: combining penetrators with a bit of Hollywood-style improvisation and our old, mostly useless friend, the nuclear bomb. But only if every single component of the plan is already built and sitting ready well in advance. The concept relies on a rocket in the same class as NASA's real SLS, the vehicle designed to eventually carry astronauts back to the moon, fully loaded and standing by. The instant a planet killer is detected on a collision course, that single rocket launches to intercept it. After roughly 5 nerve-wracking months traveling through empty space, while life on Earth carries on nervously below, it finally reaches its target somewhere just beyond Mars's orbit. There, it deploys 5 massive penetrators in careful sequence, each one positioned exactly 2 kilometers behind the last. The engineering precision this demands is genuinely brutal, and there's no room for a second attempt, which is why a small crew of extraordinarily brave astronauts would need to make this a deliberate one-way trip, staying behind to personally supervise the sequencing with no realistic way home. After tense hours of the entire world watching screens and skies together, the moment finally arrives. The icy mountain of death comes into view, and almost instantly, it's already there. Slowed down again for a closer look. The comet slams into the first penetrator at 140,000 kilometers an hour, releasing roughly 2,000 tons of TNT worth of energy in an instant. Ice, rock, and tungsten all liquefy simultaneously as that energy burrows dozens of meters into the comet's structure. The second penetrator strikes the exact same spot moments later, punching further into the same crater, melting and drilling deeper still. The third and fourth repeat the process again, carving a tunnel roughly 100 meters deep into the comet, which, on an object this massive, still amounts to little more than a surface scratch. The comet itself remains fundamentally intact. Then comes the fifth and final penetrator, carrying its real payload, 300 megatons of nuclear warheads, roughly 20,000 times the energy of the bomb dropped on Hiroshima. It travels deep into the freshly carved tunnel and detonates just before reaching the very end. This time, unlike the earlier failed head-on nuke attempt, the explosion actually works, because instead of releasing its energy uselessly into open vacuum, it's now surrounded on every side by dense rock, gravel, and ice, which trap and redirect that force back into the comet itself. On top of instantly vaporizing everything nearby, the resulting shock is severe enough that a frozen object billions of years old is torn apart from the inside out, disintegrating into millions of fragments scattering in every direction. Humanity survives. Pulling this off in reality would demand a genuinely unprecedented level of planning, coordination, and split-second precision. But the remarkable part is that it wouldn't require any speculative future technology to attempt. Every individual piece of this plan, the rockets, the tungsten penetrators, the nuclear payload, the engineering, already exists in some form today. What's actually missing isn't the technology itself. It's the decision to build and stage it in advance, before we ever actually need it. That's really the core of why this whole topic matters, even setting aside the raw, destructive numbers. This is a genuinely rare case where the probability of disaster in any given year is vanishingly small, but the potential cost, if it ever does happen, is close to unlimited. The permanent end of pretty much everything humanity has ever built. Most of the systems we build insurance and safety margins around, earthquake codes, vaccine stockpiles, backup power grids, deal with risks that are common enough to feel intuitively worth preparing for. Planet killer impacts sit at the opposite extreme, almost impossibly unlikely in any single year, but with a downside so total that even a very small probability, multiplied against it, still comes out looking like a genuinely serious, expected cost. That's precisely the kind of risk humans are historically terrible at taking seriously, right up until it stops being hypothetical. Having a workable plan and the hardware to execute it, sitting ready before we ever spot a real planet killer, isn't Hollywood excess. It's just taking that math seriously while there's still time to do something about it.